Alright, hello everyone. Hopefully you can hear me, you can hear my audio. If not, go ahead and let me know in the chat. Or if you can hear me, let me know in the chat. I'll just wait a few more minutes for people to pour in. Okay, I have someone here saying hi, all good here, so I assume that means people can hear me. Hello and welcome everybody who is joining. Hello, good to be here. I'm glad it's good to be here. All right. Gonna wait a couple more minutes. Hopefully everybody is ready to learn about spectroscopy and astronomy. Alright, I'm going to go ahead and start the recording, and I'll just kind of let people trickle in while the presentation is going on. So yeah, hello everyone, welcome to the virtual Planetarium night at UCLA. Unfortunately, it does have to be virtual due to the surge in cases, but I will try my best to bring you a good educational show today. So today we're going to be talking about spectroscopy in astronomy. Alright, so I'm just going to go ahead and get started with the presentation. Before we go ahead, I have another monitor here where I can see your questions. So if you have questions at any point, let me know by typing in the chat, and I'll try to keep my eye on the chat and see if I can answer anything that maybe isn't clear. So yeah, let's go ahead and get started. So spectroscopy, right? This is the field of astronomy that we're going to be talking about today. And so you might have seen this title and wondered to yourself, what exactly is spectroscopy? Well, it has the word, kind of the root word spectrum in there, and that's exactly what it's studying. We know light exists on a spectrum with various different colors, right? And so spectroscopy is the study of the spectrum of light. And so to the right, I've kind of put a visual here with all the colors of the rainbow ranging from red down to violet, and all of that is what we consider the visible spectrum. It's the part of the spectrum, it's the light that we can see with our own eyes. It's visible to us. And so everything that you see in the universe, you know, your chair, your desk, your phone, everything that you see is a combination of all of these colors. So it encompasses everything we see. So very important to understand. So considering that we're studying spectroscopy, which is the spectrum of light, we want to know what exactly is light, right? It's not something you can touch, it's not a solid, liquid, whatever. So what exactly is it, right? We see light every day, but we want to know what light exactly is, and it's a form of something called electromagnetic radiation. It's a lot of words. Electromagnetic radiation. What does that mean? It's got electric and magnetic in the word, so it's made up of electric and magnetic fields. And you may actually be familiar with some examples of electric and magnetic fields in everyday life. So I'll go ahead and go over some examples of those really quick. So you might remember I don't know, some instance where the hairs on your head start to stand because of static electricity. And that's an example of electric fields in everyday life. The charges that are in your hair, when your hair is standing up like that, what's happening is that the charges in your hair are repelling each other due to electric fields. So electric fields are causing your hair to stand up. Another example is when you take a balloon and you rub it on your hair, what happens is that the electrons in your hair will go out of your hair into the balloon. Then the balloon is negatively charged, your hair is positively charged. That creates an electric field, and when you stick those two together, when you stick the balloon on your head, the balloon will be attracted to your head, and they'll be held together by an electric field. Now moving on to a magnetic field, right? Magnetic fields are things that we encounter in everyday things like fridge magnets, for example, right? Magnetic fields are responsible for keeping the magnets stuck to the door of the fridge. Another way to visualize magnetic fields is to get a bar magnet with a north pole on one end and a south pole on the other end. And you can see in the diagram in the bottom left, what happens is that the magnetic fields kind of come out of the north pole of the bar magnet and go into the south pole of the bar magnet. And a way to visualize this in real life is to take some iron shavings and kind of sprinkle them all around the bar magnet. And you can see the actual magnetic field lines around the bar magnet. So those are everyday examples of magnetic fields. Okay, so when we're talking about electricity and magnetism, we have to realize that these two things are fundamentally connected, right? We call it electromagnetism for a reason, because every time you have, let's say, a changing electric field, you're going to get a magnetic field. And if you have a changing magnetic field, you're going to get an electric field. And you can arrange these fields in a way where you have a wave-like oscillating electric field, and then perpendicular to that you have a wave-like oscillating magnetic field, and we call those electromagnetic waves. So you can see kind of an animation of what that looks like to the right hand side, where on horizontally you have the blue magnetic field moving in a wave, and then vertically you have the red electric field kind of moving in tandem with it as the energy kind of propagates forward, right? And so the big takeaway from all of this is that light is like a wave. It has these wave-like properties that are going to be really important when we're discussing spectroscopy later on. Right. I'll pause for a couple seconds just to see if there are any questions and to make sure people can hear me all right. And if not, I will continue forward. There's a little bit of a lag in the stream, so I will keep my eye on chat. So the biggest thing that I really want to drive home is light is what we use to understand the universe, right? When you look up in the night sky and you see the moon, stars, different planets, what exactly are you seeing? You're seeing light. It's the biggest way that we understand what's going on in our universe. And not only is there what we can see with our eyes, but there's so much more information than what we can gather by just looking up. And that's where instruments really come in handy to help us discover what we want to discover. And the most powerful thing that we do is to combine our knowledge of physics and our knowledge of our observations of what we're seeing in space, and to put those together to paint a picture of what's going on in the universe. And that's really at the heart of what astrophysics is. And I see a question in the chat. Was this described as the left-hand rule? Let's see. Are you referring to this animation right here? If so, I think you might be referring to the right-hand rule, where you have an electric field. Let's see if I remember it. You have an electric field and a magnetic field, right? And that's your pointer and your middle finger, and then your thumb will be pointing in the direction that the wave propagates. That might be what you're referring to. Let me know if that's the question you were asking. But yeah, moving on. So in order to study light, we have this tool that we broadly refer to as spectroscopy. So again, like we said, light has these wave-like properties. And we also know that light can have different colors. The chat says yes, good, awesome, glad I was able to answer that. Where were we? Colors. So light has all these different colors to it, and we want to know what exactly gives light its color. Well, we can focus our attention on the diagram to the right-hand side, where you have red on the top and orange or violet on the bottom. And what you'll notice is you'll see kind of these wave patterns, and I want you to imagine that those are the waves that we saw in that animation a couple slides ago. And another thing that you'll notice is that these waves have a property called a wavelength. That's just the distance from one peak to the next. And you'll notice that for the red light, the distance between the peaks is relatively long. And as you go down the spectrum from orange, yellow, green, blue, violet, you'll notice that the distance between those peaks gets much and much smaller. And that's what gives light its color property. Light has different wavelengths in those electric and magnetic waves, and depending on the wavelength that it has, our human eyes are going to perceive those as different colors. So in spectroscopy, what we look for is we look at a source, and then we want to know, okay, what are the wavelengths of light that are being emitted by that source? And so I just wanted to give sort of an idea of how exactly that works by using an example of a glass prism, right? So when you're looking at any light source, unless it's specifically like a monochromatic laser, for example, it's made up of many colors. It's not just one color. So to see what colors it's made up of, you have to take that light and kind of disperse it. And that's done. That can be done with a glass prism or a grism, spectroscope, whatever instrument that you're using. So, looking at the diagram, let's follow it from left to right. Right, we start at this window shade that has a hole in it, and we're going to imagine that some sunlight is able to come through that hole and hit the glass prism. And once it enters the glass prism, the different wavelengths of light are going to bend differently inside the glass prism, and then exit at different heights. And then we can kind of capture the different colors at different heights on a white card. And that way you can see the whole spectrum and all the different colors that compose the light. Right. So at this point you may be asking, right, well, okay, spectroscopy lets us see a bunch of pretty colors, but how does that help us in astronomy? And it turns out that there is a myriad of ways that this can help us in astronomy, right? So some examples that I can name right now are spectroscopy have helped us discover the expansion of the universe. It allows us to know exactly what the chemical composition of exoplanet atmospheres are. It allows us to know the compositions of clouds that eventually form stars. We can use it to set up a system of classifying stars. We can detect motions of binary stars and motions of planets around stars. And we can detect chemical compositions of gas clouds and galaxies and a whole bunch of different things. So it's a really powerful tool. So let's go ahead and dive into one of the major parts of spectroscopy, which is measuring speeds. So I want to go ahead and familiarize you with something that we call the Doppler effect. So you may have been, let's say you're walking on the sidewalk one day, and all of a sudden behind you, you hear maybe an ambulance siren or a really loud car, and it sort of sounds like it's really high pitch as it's coming behind you, and then it zooms by, and all of a sudden the siren sound or the car sound sounds kind of lower. It lowers in pitch. So as it's approaching you from behind, it sounds higher, and then as it goes by you, it sounds lower. And this is something we refer to as the Doppler effect. Right. And so this is a property of waves, right? So let's look at the diagram. If you were standing next to an ambulance, and you were just, the ambulance was parked and it was making a bunch of noise, it wouldn't be anything particularly special about it. But looking at the bottom panel now, let's say the ambulance is moving towards you. What's going to happen is the sound waves are going to be sort of compressed, and the wavelength of the sound is going to get shorter, and then that results in you hearing the pitch as a higher pitch. Conversely, if the ambulance is moving away from you, then those waves are going to be kind of stretched, and the wavelength is going to increase, and you're going to hear a lower pitch. And because light has these wave-like properties, it works the same way. Light also obeys the Doppler effect. So what does this look like for light? Well, let's go ahead and look at this diagram to the right. So on the top panel, we have some example star moving away from somebody. And because the star is moving away from somebody due to the Doppler effect, the light being emitted by the star, the wavelength is going to be sort of increased, and it's going to look redder to the observer. And let's look at the converse situation where a star is moving towards somebody, and because of the Doppler effect, those light waves, the wavelengths, are going to be shrunk. And because those wavelengths get shrunk, you're going to see the light as being more blue. And so we refer to this as red shifting and blue shifting, respectively. Okay. So in a sense, you could think of spectroscopy as sort of our cosmic speedometer that we can use for objects in space for which we can obtain spectra. And a really famous example of the way that this was used was in 1929 by an astronomer named Edwin Hubble. And he observed the spectra of 24 different galaxies. Right? And as he was collecting these spectra, what he found was that most of the galaxy's light was redshifted. He thought, that's pretty peculiar, right? Why would most of the sample be moving away from us? And not only did he find that most galaxies were moving away from us, he found that the more distant a galaxy was, the more redshifted it was. So in essence, what he found was that the closer a galaxy was, yes, it'd be moving away from us, but then the more distant galaxies that he observed, they were moving faster and faster. And so this led to the discovery that the universe is actually expanding, which is a super cool realization, and one that began with spectroscopy. Okay. Give a couple of seconds to pause, see if there are any questions. And if not, we can go ahead and move on. And I'll keep my eye on the chat. Okay, so we found that spectroscopy can be used as sort of a cosmic speedometer, but there's another really important use for spectroscopy, which is determining what are the chemical elements that are present in the universe. So let's say, for example, on the left hand side of the screen, we have, let's say, a continuous spectrum, white light, just a flashlight or a bulb or something. And we pass that light through our spectrometer, prism, or whatever, and we get the spectrum that we see on the right-hand side of the screen, right? This is typical rainbow, something that we've seen, in everyday life, something that we're used to. And now what we can do, let's go ahead and do something interesting. Let's take a hydrogen lamp. And what that is it's this glass tube filled with hydrogen gas, and then on either end we apply a voltage, and that excites the hydrogen atoms and causes them to glow. Right? So we've got this glowing hydrogen lamp, and we're going to put that through our spectrometer, put that through our prism. And what are we going to see? Well, it turns out we're not going to see this rainbow that we typically see with a lot of light sources. We're going to see something like this, right? And instead of this continuous spectrum, we have these lines we call emission lines at very specific wavelengths, right? We call this one, for example, we call this one H alpha, and this one's H beta, H gamma. We call all these the hydrogen Balmer series. So we get these very specific lines at very specific wavelengths, or in other words, the hydrogen lamp emits only at very specific colors. Well, let's replace that with a helium lamp and see if we get anything different. So we turn on the helium lamp, pass it through our spectrometer, and we get this, right? And again, what we're seeing is these emission lines at very specific wavelengths, or in other words, we're seeing very, very specific colors being emitted by the helium lamp, but the pattern is different from that of the hydrogen lamp. If we go back, there are only a few lines in the hydrogen lamp, and then in the helium lamp there's a bunch more, and they're at different positions. Well, let's try it again once more with the Mercury vapor lamp, right? So we'll turn on our Mercury vapor lamp, pass the light through Prism or Spectroscope or whatever you'd like, and we get this series of lines. All right, so the point I want to drive home is that based on what chemical element that you're observing, if you can somehow excite that chemical element to glow on its own, then what you can get are these really specific emission lines at specific wavelengths that serve as this sort of chemical fingerprint. And it's not just these three elements that I've shown, it's every element on the periodic table has its own unique chemical fingerprint that we can measure and analyze using spectroscopy. And it's unfortunate that this is virtual, because if it was in person, I would have tried to set up some lamps so you could actually see this with yourself and hold, a spectroscope in your hands and observe these lines. But I think I'm hoping that I can convey the gist virtually. All right, so you might be wondering, okay, how can we use this in astronomy? Well, let's say we have a continuous spectrum source. Let's say we have a star or something, and then we have a cloud of gas. Well, in the case of the lamps, the hydrogen or whatever atoms were being excited by a voltage. In the case of things in space, a cloud of gas could be excited by starlight, right? So let's say we have some starlight exciting this cloud of gas, and then the cloud of gas starts to glow and emit. And what we see from that cloud of gas is these spectral lines. And when we observe those spectral lines, we can compare them to what we know hydrogen or helium or whatever to look like. And from there, we can deduce not only what chemical elements are present in that cloud of gas, but we can also determine the ratios. Like we can, for example, we could determine, okay, based on these, emission lines, based on this chemical fingerprint and how bright the lines are, I can tell there's, maybe 90% hydrogen and 10% helium, or whatever combination of chemical elements that are composing that cloud of gas. And another really important way that we can analyze gas clouds is if they move in front of that continuous spectrum source, right? So what we see, instead of those bright line spectra on the very bottom, what we'll have is this continuum spectrum, except there will be these very specific colors that have been kind of cut out of the spectrum. But we also notice that these specific colors are the exact same colors as the emission spectrum, right? The fingerprint looks exactly the same. And so we can deduce, okay, this cloud of gas contains, this much of whatever chemical element. Okay. Yeah, so in that way we can determine what's in a gas cloud or a galaxy. And we refer to the different kinds of lines as emission lines or absorption lines. And I see we have a question in the chat. How do you distinguish a source of light, a star or a cluster? How do you know if it is a single body? That's a good question. So a lot of times if you, let's say for example, you have a really big telescope that's however large, the primary mirror is however large across. You can determine, okay, if my mirror is this big, then I'll be able to see objects this tiny. And so that really tells you, never mind, you answered the question. Okay, well, I answered the question. Well, I'll finish with my explanation. If you have a really big mirror, then you can see smaller and smaller things. And so you can be, with a bigger and bigger mirror, you can be more and more certain that objects aren't being blended together, for example. So if you have two stars that are really close together, if you have a tiny telescope, they're just going to look like one point source. But if you have a really big telescope, then you'll be able to distinguish the two. So distinguishing a source of light just depends on, number one, how big your telescope is and how confident you are that you can distinguish sources. And you can also use spectroscopy. Like if you see two sets of emission lines that are Doppler shifted differently, then that means there are two speeds within that one source. So then you can say, oh, well, if there's two speeds, there's two objects. Hopefully that makes sense. Okay. In terms of the way that we analyze spectra in astronomy, we don't usually look at spectra that kind of look like this rainbow shape or this rainbow pattern. We'll typically put it on a graph where the wavelength of the light is on the x-axis and the brightness of the light is on the y-axis. And these spikes that you see on the graph correspond to those very specific colors and those very specific emission lines that we see in our colorful spectra. And so just to give you another way to visualize it, right, if I were to take my helium spectrum and place it right underneath this graphical spectrum, you can see, for example, that bright orange line at 587.4 nanometers corresponds to that particular peak on the graph, and then you can see kind of that forest of other peaks to the left, more towards the blue and the violet. So when we're looking at spectra, we typically don't look at them in this beautiful color image format. We usually look at them as like as a graph. Right. So getting into the specific ways that we use this in astronomy, we can, for example, see all of these spectral emission lines for different elements when we look at the spectrum of a galaxy, which is close to the work that I do here at UCLA with my advisor, Dr. Shapley. And what we can do is you can see that this team of scientists has kind of annotated this spectrum that you see on the right-hand side, where you see this like O and then the Roman numeral 2 and then NE Roman numeral 3. Those are the ways that we label elements in astronomy. So that would be oxygen, neon, hydrogen, nitrogen, sulfur, argon. We can detect all of these chemical elements in the gas of these distant galaxies, and we can use the brightnesses of those different emission lines to determine, okay, how much of this particular element is in the gas in this galaxy. Another way that we can use, another way that spectroscopy is useful is it's how we've been able to determine what the sun is made out of. So again, going back to that picture of the cloud going in front of the star and kind of snipping out or cutting out specific colors from the spectrum, we can get something similar when we're looking at the atmosphere surrounding the sun. And that's what we're looking at in this image, right? So you can see all these sort of horizontal bars of different colors and these different wavelengths being absorbed. And what we're actually looking at is a super long spectrum that if I were to unravel it, it would be much, much wider than the screen. And so in order to show everything, they've just kind of taken it in sections and snipped and stacked on top of each other. And we can see that there are so many absorption lines and different spectral features on this spectrum of the sun. And when we analyze those features, we can tell the properties of the atmosphere of the sun. And another really cool thing that I think is awesome is that we are able to detect kind of the chemical compositions of atmospheres of exoplanets or planets that orbit stars other than the sun, right? So from this particular figure on the right-hand side here, we see that this planet has maybe some aerosols, methane, hydrogen cyanide, and we can detect that just based on the spectrum, right? And the way that works is the planet will be orbiting around the star, and then it'll pass in front of the star. And what happens when it passes in front of the star is that the planet's atmosphere will start absorbing part of the spectrum of the star, and based on those absorptions, we can tell what is in the planet. Okay. And so if we can tell kind of what the compositions of planetary atmospheres are, that's really exciting and important for our search for habitable planets, right? Does this planet have water? Does it have oxygen, nitrogen? Does it have the essentials, or is it emitting organic compounds? It's another way to search for life. And so I kind of want to emphasize, this throughout this whole presentation, I've sort of hyper-focused on the visible light part of the spectrum, right? That's the part of the spectrum that we can see. But, what happens when we go beyond, let's say, ultraviolet, for example? How can we get bluer than blue? What happens there? And it turns out we can. We can detect ultraviolet, X-rays, gamma rays, cosmic rays. And what if we go to the other side? What if we go redder than red? Well, that's when we get into the infrared, microwaves, radio, all these kinds of things. And the part of the spectrum that we can see is only just a sliver. It's the tip of the iceberg. But astronomical instrumentation allows us to probe a significantly larger part of the spectrum than we can with our own eyes, which yields a ton of information for us as scientists. So I just want to go ahead and leave this summary up here. I'll go over it, right? So we went over today that light travels in these electric and magnetic waves, right? And we use spectroscopy, right, studying the specific wavelengths of those waves in order to study light in space. And so one of the big uses for spectroscopy is that we can measure speeds in space, and that's how we initially discovered that the universe was expanding. Additionally, we can use spectra to detect chemical elements, right? We can determine the chemical composition of something just by looking at the light that it's emitting, or maybe the absorption from background sources that it's performing. And at the end of the day, the visible part of the spectrum is just a small piece of the puzzle, and there's so much more of the electromagnetic spectrum that we use to understand what happens in space. And so that's it for the presentation portion of the Planetarium show. Does anybody have any questions? And kind of while I'm waiting here, I'm going to go ahead and set up the next portion of the show. Let's see, how related is spectroscopy of the atmosphere of a planet and the analysis of the chemical composition of its surface? That's a good question. It might be a better question directed towards somebody who studies exoplanets, but I'll take a shot at it. From what I know, the main features that we're looking at when we're looking at a spectrum of a planet that's moving in front of a star, the main feature that we're looking at is the absorption being performed by the atmosphere of that planet. So if we go back to this slide right here, right, these features in the figure in that planet's spectrum come from the atmosphere. So that's the only thing that we can say directly. Now, in terms of how connected the composition of a planet's atmosphere is to, the composition of its crust, truthfully, I don't know. But, yeah. Hopefully, maybe that clears things up. And if not, let me know. Let's see, isn't it true that if light from a star passes near a massive object, its light will be redshifted? Sort of. So, let's see. There is, maybe not redshifted, but, okay. So when we describe light passing near a massive object, what we're really describing is light's path through space and time, right? Because of the mass of that object, it kind of bends space and time, and it bends the trajectory of the light. So when light passes by a massive object, its trajectory can actually be changed, and light can kind of change directions. I know that there is also the existence of what we call gravitational redshift, where light can the wavelength of light can be changed in the presence of a gravitational field. Maybe one of those things is what you're referring to. Let's see. Did you say you're researching gas clouds in other galaxies? What are you learning about these galaxies from that research? Yeah, so what I'm researching, these are all great questions, by the way. What I'm researching is what's called the Interstellar Medium, or ISM. So every galaxy, I'm sure you've seen images of galaxies. Let's take a spiral galaxy, for example. It's made up of a whole bunch of stars and gas and dust. And the stuff between all the stars in a galaxy, the gas and the dust, is called the ISM, or the Interstellar Medium. So what I'm studying isn't just individual gas clouds in galaxies. I'm studying the stuff, all the gas that makes up that galaxy, if that kind of makes sense. So what are we learning about the galaxies from that research? Well, one of the big things that's important to know about galaxies through the research that I do is how their chemical composition changes over time. Right, so the picture of galaxy evolution right now is that you start off with these galaxies that are mostly made of hydrogen, and then that hydrogen slowly forms these gas clouds that collapse and form stars. And when you form stars, right, stars go through their lifetimes, they burn through their hydrogen and make helium, and then burning through helium, they make heavier and heavier elements. And then those stars die, and they release those heavy elements back into the galaxy. They recycle those elements back into the galaxy. And so as these galaxies progress over the history of the universe, we are seeing more and more heavy elements populating the interstellar media of these galaxies. Right? It's kind of like if you're looking at a lake, right? And then there's a factory nearby the lake that's kind of dumping sewage into a stream, and then you start detecting sewage in your lake. You can determine, okay, well, there's kind of this sewage inflowing into the lake. And similarly, if we look at these heavy elements that are starting to pour into these galaxies, we can figure out what are the processes going on around the galaxies, kind of regulating their growth, changing their chemical composition, things like that. Hopefully that analogy kind of made sense. And if not, let me know. I can elaborate. Chelsea says thanks. Aerospike says yes. Okay. I assume I've answered your questions. Yeah, thanks for all the questions, people. This is great. Todd says thanks. Yep, you're welcome. Okay. All right. So if there are no more questions, I'm gonna go ahead and switch over. Let's hope nothing breaks. Gonna go ahead and switch over to Stellarium. And I'm just gonna wait until I can see Stellarium on the live stream. Okay, perfect. So hopefully what you should be able to see, if it's hard to see, try turning up your screen brightness. So this is the virtual planetarium portion of the presentation. And we're using a piece of free software that you can find online and kind of play around with yourself called Stellarium. So normally during, not during COVID times, we would turn on the projector at the planetarium and kind of show you around the night sky and look at some things that you might be able to point out for yourself in the real world on a dark night. But we are virtual, so we will be using this program. And it's actually a pretty powerful program and one that I encourage you to check out for yourself. Anyway, I have to go ahead and wipe the dust off my screen, otherwise I'm going to confuse it with stars. Okay. So the first thing that you'll notice is that it's very dark. Right? We're simulating the night sky, and you'll see this red S in the center. And that tells us that we're currently facing south. And Stellarium is set up right now to show what the night sky looks like in Los Angeles. And we have a field of view of about 60.2 degrees. And rule of thumb is that human field of view is around 60 degrees. So this is probably what you would see if you were looking at the night sky in real life. Aerospike says they use Stellarium. Well, I'm glad you use Stellarium. It's a great program. Okay. Right, so we're facing south right now, and all we have to do is use the trackpad or mouse or whatever, and we can transition and slowly pivot westward. So we can look southwest, right, and then we've got this W looking west, and then we can look northwest, and then finally we can point towards the north. All right. So let's see if we can look at some interesting features in the northern sky. The first thing that I'll go ahead and point out is we can actually see the Big Dipper from here. If you look closely at this region in the sky, you can see the kind of the ladle over here, this bowl of the Big Dipper, and then the handle goes down and dips below the horizon. So if, currently in the night sky it's rising above the horizon, but we can't fully see it yet. But the powerful thing about Stellarium is that we don't have to look at the night sky right now. We can look at it at any time we want. So we'll go over to this date and time window, and we'll go, let's move it forward a couple of hours. And you can see, now we can see the Big Dipper. Here's the end of the handle, goes over here, and here is the bowl. All right. So let's say you're able to spot the Big Dipper in the night sky, and you want to know, okay, what direction is north? Well, the way you can find out which way is north is by looking for the North Star, or Polaris. So the way you do that, let's say you don't have these, red N and red NE markers, because, as far as I'm aware, most people don't have these in their field of vision. And you want to know where north is, right? So let's look at the end of the Big Dipper at the edge of this bowl, and look at these two stars here and use them as a pointer. And I'll follow these two stars all the way to the North Star, Polaris. And if I click on it in Stellarium, it'll give more information than I could ever possibly know what to do with. But this is how you can navigate. This is the North Star. It always is in the same position in the northern part of the sky. And so let's look for the constellation Cassiopeia. That's another bright one that you can usually see even if the conditions aren't too great in the sky. So here's the Big Dipper, here's the North Star, and here's Cassiopeia. They're usually opposite sides from the North Star from each other. All right, so here are the 5 stars. It makes sort of an M pattern. 1, 2, 3, 4, 5. That's Cassiopeia right there. All right. And so let's say you don't exactly know how to find all of these constellations in Stellarium, but you really want to know what they look like. You maybe heard of this constellation in passing somewhere, and you want to know, okay, how do I figure out where this is? Well, you can just kind of go down here, and Stellarium has this wonderful feature where you can add constellation lines to the sky and constellation names. And there you go. We have the North Star at the very tip of Ursa Minor. Then we have the Big Dipper as part of Ursa Major, and Cassiopeia right over here. All right. Now let's turn these off for just a second. All right, so we've got the North Star, we've got Cassiopeia. Let's start looking towards the west, and what starts to come into view is a very interesting feature. You might be able to see it right here, is this kind of fuzzy blob. And early astronomers kind of didn't really know what to make of this. All they saw was just this fuzzy blob in the sky that doesn't look like these point sources around it, which are stars. All right, and so as you zoom in a little more, right, you can start to see the blob a little bit brighter. And what's really interesting is, if you think about being in the shoes of early astronomers, they're thinking to themselves, all right, what is this giant nebular looking thing? They actually called it the Andromeda Nebula because it looks like a cloud, and they didn't really know what it was. And so if you follow the literature on what scientists believed that this object was throughout history, it turns out that spectroscopy played a very important role in discovering that this blob isn't just something that's like a cloud nearby Earth. It's actually a whole galaxy about 2 million light years away. It's the Andromeda Galaxy. And one of the clues that was used to figure out that this is actually a galaxy outside the Milky Way is by using its Doppler shift. Right, if you take the spectrum of the Andromeda Galaxy and you measure its Doppler shift, you find out that it's coming towards us at about 300 kilometers per second, right, which is much faster than the orbital speeds in the Milky Way, right? So it's going faster than anything in the Milky Way. It's unlikely that it's part of our galaxy, right? So that was one of the clues that scientists started discovering to say, hey, this is something that's outside of the galaxy. And that is, that's kind of along one of the early steps leading to the field of extragalactic astronomy, right? But anyway, in Stellarium, right, we can sort of zoom forward in time to the 21st century, where we have wonderful telescopes that can take these beautiful images, and we zoom in and we see so much detail, right? We see these dust lanes and this kind of glow around the galaxy caused by just an ensemble of starlight. We even see that the Andromeda Galaxy has a couple of these tiny little neighbors. Let's see. Stellarium is great for following comets too. Is it? I know it does. I think like satellites and stuff, but I didn't know it does comets. But that's good to know. All right, so we're gonna zoom back out to 60-degree field of view. There we go. And let's see what else we can spot in the sky. There's something. Right, so if you don't see it already, here's something really cool. This is the Orion Nebula, and it's I should say the Orion constellation. And it's a very bright constellation. You can see it even in my apartment here in Los Angeles, which is just plagued by light pollution from the city. I can still see Orion, so it's a really bright constellation. And another little navigation trick that you can use with Orion is kind of looking at Orion's posture. To help see what I mean with this, I'm going to turn the Constellation Lines on, and you can kind of see that Orion, when I'm looking at it, sort of looks like it's standing upright. And so if it's standing upright, that means we're looking south. Right? So to confirm that, let's go down to the Stellarium horizon, and yep, we are looking southwards. So if Orion is upwards, that means you're looking south. Well, let's change the time of day by a few hours. Right. Okay. Right. So let's say you're looking at Orion now, and you notice Orion's sort of tilted towards the right, and you can see the sword of Orion is also tilted. Well, if Orion's tilted to the right, then that means you are looking in like the southwest direction. So we can confirm that with Stellarium, and yes, we're looking sort of west-southwest. Now let's move the time backwards to see converse example. All right, we're gonna move in the sky. All right, so now Orion is sort of tilting back. It's tilting to the left. And what that means is that you're looking more towards the east. So we can confirm using Stellarium, and yep, we are looking southeast. So that's a neat little trick that you can use if you can find Orion in the sky, it's a very bright, very easy constellation to spot. Then you can kind of orient yourself in the cardinal directions. Okay. Well, what if let's say we want to get a good glimpse of the Milky Way galaxy, right? How do we do that? Right? It's not very easy to see it from the northern hemisphere. So what we can do is we can go ahead and change our location. So let's go down to, I don't know, somewhere in Chile. Choose an arbitrary location in the southern hemisphere. And we can look around and try to spot the Milky Way galaxy. Let's see. Might also help to change the time of year. So we're going to go and change the time of year to August. Let's change it to August. Okay. And there we go. When we're in the southern hemisphere in August, we can get this really clear image, or this really clear view of the Milky Way galaxy, right? And the reason that it looks like this band in the sky is you can imagine a spiral galaxy is like a pancake, where you can look at it face on and see it as sort of this circle or this round figure like you see in those images. But then when you flip it and look at it edge on, it kind of looks like a line or a band in the sky. And so that's why we see the Milky Way as sort of a band streaking across the sky. Right. Okay. guess there's one more cool thing I wanted to show you in the southern hemisphere. Actually, a couple more cool things. Here we go. So these two stars here, sort of by the Southern Cross constellation, we're looking southwest. What we can see here are these two stars here. They're labeled here Radial Centaurus and Hadar for some reason. But two other names, or more common names for these two stars, are Alpha and Beta Centauri. And these two stars are actually the closest stars to us other than the Sun. And you can only see them from the southern hemisphere. So if you're ever in the southern hemisphere, these are definitely two very cool things to check out. Let's see, and then one more object that I like to kind of focus on. Two more objects that are right here. You might notice these two kind of fuzzy looking things, and these are the large and the small Magellanic clouds. And these are two irregular small satellite galaxies of the Milky Way, right? They're really close to the Milky Way and they're small, but because they're so close, we can see them really big in the sky, and they have a lot of detail when you zoom in. Right, so this is the large Magellanic Cloud. You can see all those stars in the cloud or in the galaxy. And then you can look at the small Magellanic Cloud and see all the details and things in that cloud. Right. And you can see a globular cluster right here. Yeah, those are the main highlights I wanted to show in Stellarium. Are there any other particular objects that people would like to see, or locations people would like to travel to in Stellarium? It says, interesting how astronomers figure what objects are in our galaxy. Is that how they figure what stars belong in clusters? Well, in terms of figuring out what stars belong in clusters, I'm pretty sure we can just kind of figure out, like if it's a globular cluster, you can just see which stars are in the vicinity. Let's look at an example globular cluster. Like over here, for example, you can for the most part make out which stars are part of this globular cluster. Maybe on the edges here, I'd actually be curious to know how they distinguish some of these stars. Usually you can tell because they all have like a similar chemical composition, because they're thought to form from the same stuff. Let's see. Hopefully that maybe answers your question. And they can also measure, radial velocities for the stars. So if two stars next to each other have much different velocities, then we can say, those two stars are probably in different parts, or are actually probably farther apart. They're not next to each other. We can also use techniques like parallax, which is essentially the idea where as the Earth goes around the Sun, then our view of the stars will kind of shift around, and we can see which stars are closer and which stars are farther. So we can sort of build a 3D map of where all the stars are. So that's another way we can figure out which stars are part of our galaxy or part of a particular cluster. They should be around the same age. Yes, they should be around the same age when you're looking at stars in a globular cluster. seems like the questions are slowing down. I'll be happy to stay on for a few more minutes in case anybody has any more questions, but for everybody else, thank you so much for coming to the Planetarium show. Thank you for engaging and asking questions, and yeah, I'm glad we were able to share this virtual experience. What would you like WST to discover? Are you referring to JWST, the James Webb Space Telescope? Well, what I'm most interested in is JWST's ability to peer into the infrared. Right? We kind of touched on in the presentation that the visible part of the spectrum is only, the tip of the iceberg. And remember how we discussed that the further away galaxies are, the more redshifted they are. Well, it turns out that the really, really far away galaxies are so redshifted that most of their light is now actually in the infrared. And so we need an infrared telescope, the James Webb Space Telescope, to be able to study those galaxies. So in terms of what I'm most excited for, I'm most excited to see the data coming from the James Webb Space Telescope looking at galaxies in the very distant universe where most of the light is reaching us in the infrared. Hopefully that tells us more information about the early stages of galaxy evolution. Just pausing in case anybody is typing up their questions in the chat and needs more time. Well, if there are no more questions, again, thank you for attending the Virtual Planetarium show. If there's something that you want to ask as a follow-up question, feel free to reach out to UCLA Planetarium's Twitter. You can reach me by email, leoclark@astro.ucla.edu. And yeah, thanks for coming, everybody.